So dear students, the force acting on a body can be either tensile or compressive. By applying the force on a body, it produces internal resistance, which is classified either as normal stress or shear stress. This depends upon the type of loading. Which are the different types of loading? The first one is the axial loading or direct loading. So this is the first one, in which the load is acting through the axis of the body. So if I have a body with the linear axis, if the force is acting through the axis, then it is called an axial loading, where stress equal to sigma equal to F by A, where A is the area of cross section. Second type of loading is bending loading. If the load produces a bending of the beam, then the bending stress sigma is given as M by Z. The body can be subjected to torsion, where tau equal to T by ZP. So these are the different types of loading. Here we can see that in all the cases they have uniform cross section. However, in practical cases we cannot ensure such uniform cross section. There will be keyways, fillets and sudden changes in cross section. In such cases we consider stress concentration. So consider this case. Here we have a shaft with a change in cross section from diameter capital D reducing to a smaller diameter small d, and here we have given as a fillet. Whenever we have a sudden change in cross section, these stress lines gets concentrated or concatenated to a small area, which produces a stress concentration, and the fracture can occur from this region. So whenever a machine component changes the shape or its cross section, simple stress distribution no longer holds good and neighborhood of the discontinuity is different. Irregularity in stress distribution due to the abrupt changes in shape or the form is called stress concentration. Now we'll study how to design the parts which are subjected to stress concentration. Such parts are designed by a factor called stress concentration factor. Stress concentration factor is defined as the ratio of maximum stress to the nominal stress. This stress concentration factor can be either found by mathematical derivation, or we can use some experimental methods. Normally we use photoelastic method to find the stress concentration factors. These are some numbers. So we will multiply these, the nominal stress multiplied by with stress concentration factor to get the maximum stress. In order to avoid stress concentration, we prevent sudden changes in cross section. See this figure. In figure A, there is a sudden change in cross section which can produce a stress concentration which can result in a crack to propagate along this plane. It will get cracked about this. In order to prevent such crack formation and stress concentration, we give a fillet, or we can increase the radius of the fillet, or we can give some grooves so that there is a gradual change in the cross section. Now we'll do a simple problem on stress concentration. Here we have a shaft with diameter 50 mm and 25 mm. They are connected by a fillet radius of 5 mm. It is subjected to a tensile load of 12 kN, and we have to find the maximum stress induced in the following case, taking the stress concentration into account. Here we can see that it is subjected to tensile force. So from our equations, we will select the one which is suitable for our one, that is for direct stress, sigma max equal to F by A into KT. Here F is the force acting, A is the area of cross section, and KT is the stress concentration factor. So I will write that equation: sigma max equal to F by A into KT. That is equation 2.1 A suitable for axial loading or direct stress. Here F is the load acting on the body, F equal to 12 kilonewton, 12 into 10 power 3 Newton. A is the area of cross section. Here we have two cross section. We have to find the maximum stress. So the maximum stress will be acting at the minimum cross section. So minimum area will be pi by 4 into 25 square. Now here the only unknown is KT, stress concentration factor KT. How to find KT? We find it from the dimensions. So here we have R equal to 5 mm, D equal to 25 mm and capital D equal to 50 mm. So we have to select from the data book a suitable figure matching to our problem. So from page 42 we can see that from figure 2.23 there is a stepped shaft which is under tension, which is similar to or which is same as our question. So in our question we can see that the fillet radius is 5 mm. Now we can use this graph. Okay. So here on the x-axis it is given R by D. First we will find the value of R by D. What is the value of R? R is given as 5 mm and small d equal to R equal to 5 mm and d equal to small d equal to 25 mm. Therefore R by D equal to 5 by 25 equal to 0.2. So I can find that point on the graph. Point 2. So this is the point of our reference. So this is a point for our reference, that is R by D equal to 0.2. Now we have a number of curves corresponding to different values of capital D by D. We have capital D and small d values. Capital D was about 50 mm and small d was equal to 25. So capital D by small d equal to 50 by 25 equal to 2. So among these, this curve matches our problem. Now the step is very simple. We have to plot this line vertically upwards to join to meet at this curve, and projecting it to the y-axis we can see that it is just below 1.65. So I can take that value KT equal to 1.64. So going to my previous equation, sigma max equal to F by A into KT. F equal to 12 kilonewton, 12 into 10 power 3 Newton. A is the area of cross section, minimum cross section area, pi by 4 into 25 square, and KT equal to 1.64. After substituting, I will get sigma max equal to 40.33 Newton per millimeter square. Okay, thank you for watching.